Hey everyone, it's Mrs. Suderman again, and this time we are going to be looking at determinants and inverses of matrices. If you like, you can check out Chapter 4, Section 4, and Section 5 in your textbook for extra information or additional examples. So just a heads up, we're going to be finding the determinants and inverses of 2 by 2 matrices. Every square matrix n by n, meaning same rows and same columns, has an associated value called its determinant shown by straight vertical brackets such as this 1, 2, 3, 4. So instead of seeing the brackets with the little corners on them, we now just have the straight vertical brackets. And notice this is a 2 by 2 matrix, so it has the same number of rows as it does columns. The determinant is a useful measure, as you will see later in this lesson. To calculate the determinant, here is a little table to help you remember. You can write this down if you like, but if we have the matrix 1, 2, 3, 4, and we are looking for the determinant, we're going to take the difference of the products of the diagonals. In other words, as you see, which is color-coded here, this 1 times 4, those two things are multiplied, and then we subtract the product of the other diagonal. By the way, the determinant of matrix A may be denoted as DET A or A with the straight vertical brackets around it, but please don't get that confused with the absolute value notation. Those two things are not the same. So let's look at an example. We're going to find the determinant of each of the following matrices. So here's one. We have 1, 5, 4, and 8. So to find the determinant, we are going to need to take the difference of the diagonals. So here's this color-coded thing. We're going to take 1 times 8, and we're going to subtract 4 times 5. Notice the brackets have now changed to the vertical line brackets as opposed to the ones that had the corners before. Okay, so we have 1 times 8 minus 4 times 5, which then when we multiply that out, we get 8 minus 20. So therefore, the determinant is negative 12. So the determinant of this matrix is negative 12. We can also have a matrix that has pi in it. We can leave it in terms of pi, that you don't have to multiply it out and round it. You could also have matrices that have letters. I mean, anything is really possible here. So for this one, we're going to do the same thing. We're going to multiply the diagonals and take their difference. So we have 1/2 times 2 pi minus 4 times 1/8. Please make sure that you're always taking the diagonal that starts in the top left, and then that is going to be your first diagonal, and then the second one. As in, what I'm trying to say here is that 1/2 times 2 pi, notice that we started in the top left corner and we multiplied across, and then we subtract starting, you can think of it as the bottom left corner or the top right corner. But either way, what I'm trying to say is that you multiply the diagonals in the same order every single time. Okay, so 1/2 times 2 pi is just pi, and then 4 times 1/8 is 1/2. And so then we can just leave the determinant like that. We can get this determinant equal to pi minus 1/2. Okay, a matrix can have an inverse only if it is a square matrix. So now we're going to be looking at the inverses instead of the determinants. So square matrices, they have the same number of rows as columns. So here we have a 2 by 2 matrix, or we've got a 3 by 3. You could do this with 4 by 4 and so on. But not all square matrices have inverses. Just because they're square does not mean that they have inverses. So when we evaluate, for example, the product of 2 and its multiplicative inverse of 1/2, that will give you 1. For example, 2 times 1/2 equals 1. The 2 and the 1/2 cancel each other out just to get 1. Well, we can do the same thing with matrices. So if we multiply a square matrix, say A, by its multiplicative inverse matrix A to the power of -1, which just means the inverse of A, that will give you the identity matrix. Well, what is the identity matrix, you ask? Well, it is a matrix where it has ones on the main diagonal, starting from the top left going to the bottom right, and it has zeros everywhere else. So you can imagine that if this were a 2 by 2 matrix, we would have just 2 rows, 2 columns, and it would have just 2 number ones and then zeros on the opposite diagonal. You could do the same thing with 4s. It just must be square, 1's the diagonal, 0's everywhere else. So to figure out what the inverse of a 2 by 2 matrix is, here's how we can evaluate it. So if matrix A is given right there, A, B, C, and D, then the inverse matrix will equal 1 divided by the determinant of A times this little flip-flopped matrix. So the first diagonal got switched, the second diagonal got multiplied by -1. If you get a determinant of 0, then 1 divided by 0 will be undefined. Therefore, a matrix with a determinant of 0 has no inverse. We would call that matrix a singular matrix. So let's find the inverse of this matrix if it is defined. So of course, first we need to find the determinant. So we take the difference of the products of the diagonal, so we'll get 4 times 1 minus 2 times 3. So then we'll get a determinant value of -2, which is non-zero. So that means this matrix has an inverse. Therefore, we can proceed to evaluate that the inverse of A will be 1 over the determinant of -2 times our flip-flopped matrix, where we'll get, instead of 4, 1, we'll now have 1, 4. And then we multiply the other diagonal by -1 so that we switch the signs. And then now we just have something where we are multiplying, we have basically -1/2. We can use like a scalar product. So we distribute that -1/2 into the matrix, and there is the inverse. Let's look at another example. So here we have 4, -3, -1/3, and 1/4. Always check the determinant first. So we have 4 times 1/4 minus -1/3 times -3. Well, that equals 0. So we don't have anything else we can do here because this matrix has no inverse. And let's look at one more example of these. So here's the inverse, 3, 2, 3, -2. And we're finding the inverse. This is our matrix, and we're going to see if we can find it. So check that the determinant is non-zero. So 3 times -2 minus 3 times 2 will give us a determinant of -12. So it's not 0, so this matrix does have an inverse. So when we plug it into our formula, 1 over the determinant of A, which was -12, times our flip-flopped matrix where the first diagonal is switched and the second diagonal is multiplied by -1. Distribute that -1/12 into the matrix, and there is the inverse matrix of A.
Greetings, my algebraic comrades. I have a message for you from Mrs. Suderman. Did you take notes? Mrs. Suderman said she will be checking for them tomorrow during class. And here's the fun part. SHHHHH. Don't tell your friends, they won't be in trouble. Draw a star on the top right corner of your notes. This will let me know that you prepared for class. Also, shout out to Mitch, Vanessa, Drew, and Harry. That's all, folks, and may your evening be filled with mathematical wonders. See you lads and ladies later.